So let's add a tiny bit more detail to the extratropical atmospheric response to this diabatic heating in the deep tropics. We already implied many of the processes in terms of the waves, the instability of the jet, eddy fluxes, and so on. Looking at it more formally, the barotropic energy conversion from the climatological mean flow. So we are looking here at both the zonal asymmetry in the flow, so du bar dx, if there are regions where there is a lot of zonal stretching of the zonal winds, that can produce eddy kinetic energy. So that's the, you can think of it as shear barotropic conversion from the horizontal shears, and this is the meridional shear. So when you have net northward transport if both u prime and v prime have the same sign, right? So if u prime is positive and v prime is positive, then you have a positive, and if both are negative, you have a positive as well, and so on. So there are such details, but as we said before, we have the baroclinic instability, the zonal meridional temperature gradient, vertical shear, available potential energy, which can get converted into eddy kinetic energy. That's the baroclinic instability. And we have these horizontal shears in zonal and latitudinal directions, which can also convert to verticity. You can typically curl your fingers around the shears to get the direction of the verticity. They give the fluid air rotating tendency. So you can also look at the verticity equation here. D zeta dt is minus, I wouldn't not going into the derivation of these, but you can find them in the paper cited in the book, or books like Holton, which is a very beautifully written book, in fact. So divergence of v, which is the horizontal velocity, times zeta plus f, where zeta is the relative verticity and f is the planetary verticity. You know, because we are on a rotating planet, even if you are standing still, you have you acquire a verticity. So this is the total or absolute verticity, zeta plus f. Lots of details there, plus the forcing. So in the mid latitudes also you can have heating generating diabatic heating generating verticity, but you can also have convergence of eddy heat fluxes, right? So typically any variable x, let's say the verticity, we tend to split it into the seasonal mean, which is the climatology we're talking about for delivering the energy to eddy kinetic energy at subseasonal time scale. So L here is the low frequency or the subseasonal time scale. H is the higher frequency or the synoptic time scale. So obviously we have these multiple time scales running together, right? So then the subseasonal verticity equation can be written out of that splitting as minus divergence of VH, which is the synoptic advection of relative verticity into the subseasonal time scale. So you can think of it as upscale energy or verticity transfer from synoptic scales to subseasonal time scales, and minus divergence of the subseasonal time scale itself and residual term. Okay, so this is typically how it is done, because when you measure things, you are getting the total field. You have climatology, subseasonal, synoptic, everything mixed in, and then you are extracting these by various filtering, right? Seasonal mean is okay. For subseasonal, then you have to do a filtering of 20 to 100 days, and then synoptic scale is high pass filter of less than 10 days, and so on. So that's how you separate out the contributions, and then you try to infer whether there are transfers of verticity, in this case often energy upscale or downscale, and so on and so forth. So here's example: 500 hectopascal geopotential height response averaged between days 6 and 10 and days 11 and 15 for 80 degree east heating. So we are in the Indian Ocean in terms of the heating above here, and 160 degree east heating in the bottom. Okay, so 80 degree east 6 to 10 days, 80 degree east 11 to 15 days, 160 degree east, which is in the Western Pacific Ocean with the deep convection center, 6 to 10 and 11 to 15. So essentially, again, similar to what we saw before, you have clearly extratropical circulation response seen in geopotential height of the 500 millibar HPA surface, and you can again see the wave features. At these latitudes, any perturbation, because Coriolis is strong, is going to produce these wave patterns, right? So that's kind of the zonal asymmetry du bar dx and du bar dy terms that we talked about as well. Okay, so clearly there is an extratropical circulation response to tropical heating, and it is sensitive to the location of the heating. So you can see that these responses to 160 degree east heating seem much stronger than the response here in terms of the deepening, troughing or ridging of the geopotential height. Okay. Here is another way to look at it: projections in longitude. Normalized projection of northern hemisphere extratropical 500 hectopascal geopotential height response averaged between days 11 and 15 as a function of the longitude of the equatorial heating center's location. So depending on where the heating is here in longitude, the projection onto normalized projection onto northern hemisphere extratropical 500 hectopascal. Okay, so that's what we saw here, mostly positive and strongly negative here. Okay, so you can see maritime continent, Western Pacific into the Atlantic, and the Indian Ocean sector. So deep tropical diabatic heating can induce extratropical circulation anomalies, and to the extent that MJOs and mesos in the deep tropics are associated with these diabatic heatings, these connections, tropical forcing of extratropical circulation anomalies, can be used to achieve some subseasonal S2S forecast at high latitudes. So models are not doing that great, as we saw in the Madden-Julian oscillation case, but to emphasize the point here, for a climate model to have a reasonable response to tropical forcing and teleconnection patterns, which we want to use for predicting locally, the model should have a realistic representation of the distribution of tropical diabatic heating. That's very critical. Models tend to have biases in that. Climatological mean flow, and thus small systematic errors for Rossby wave propagation and wave mean flow interactions. So the errors cannot be too large, then you don't otherwise you will not get the teleconnections, or you will not get a good representation of them. Extratropical storm tracks and associated transient eddies also have to be done reliably in the models if you want to capture the impact of tropical thermal forcing on the extratropics. Okay, basically they have to do everything right. Okay, so let's close this podcast here, and we'll come to see how extratropics then feed back to the tropics. And we already mentioned specific places like the eastern, so this is the Atlantic here. You can see the outline of Africa here, and you can see a rendition of kind of the upper tropospheric trough, which are critical regions where this reach from the extratropics into the tropics can happen because of the wave dynamics and how they depend on the background flow and the gradients of the background flow. So we'll see how that works in the next podcast.